In this video, I'm going to be introducing you guys to integrals. What a fun topic. Not really. But what is an integral? First things first, an integral is just the area between the curve and the x-axis. So let's say we shade in all these areas between in the function here. And what actually happens for integrals is the areas above the x-axis are treated as positive areas, and the areas below the x-axis are treated as negative. So if the area of this part was 5, and the area of this part was 3, the area of this shaded region is 2, then 2 and 3 are positive numbers, so we can add 2 and 3. But since 5 is below the x-axis, we treat that as a negative number, so we subtract 5. Therefore, the net area of this integral in our domain of the drawing is 0. So how do you solve for integrals? Well, there's 3 main ways you can solve for integrals. You either use Riemann sums, basic geometry, or antiderivatives. Now the thing about basic geometry is that doesn't apply for all cases. So basic geometry can only happen if you have some nice function that looks like a triangle, or looks like a rectangle, or a semicircle. Those are a couple examples. And Riemann sums also are just approximations of the actual integral. The real way to solve for integrals is the antiderivative, which we'll be covering all 3 in this video. But let's go ahead and talk about Riemann sums first. So what's a Riemann sum? A Riemann sum basically uses in essence, a bunch of rectangles to solve for the area of your under the curve. So, what is this idea? Well, you pick some delta x, some change in x, along the x-axis, right? And then you use either the right rule, the left rule, the midpoint, or the trapezoidal. Now all of these have their own videos coming, but I'll introduce you in essence to the basic idea of what they are. So the right rule basically just picks the point to the right of delta x. So if you had some region delta x, you would pick the point to the right. You go up into the function and then draw a dot at that x value. And all you would do is draw some rectangle, and then so on. You go to the right of your delta x region, you pick that point, and then you draw a rectangle, and so on and so forth. Right? Just draw a bunch of rectangles. Now, the thing about this is, again, it's just an approximation. It's not the actual integral of your curve. But basically, what you can do is find the y value of each of these points. Right? Each of these points I drew out. And when you find the y values, all of those, you can assign them, let's call this y1, let's call this y1, this y2, this y3, and this y4, and each of them are the heights of the rectangles. Well, here's the thing about the formula of a rectangle. It's height times width, and you have the width. Width is delta x, and it's the constant that you chose for this problem. So you can multiply y times delta x for each of these in order to get the area of the rectangles, and then add them all together. And the thing is, if your y value is convenient about this, is if your y value on the function is below the curve, the y value will be negative. So you can treat that as a negative area as well. That's the right rule. What's the left rule? Well, the left rule is very similar to the right rule. You just have some delta x values. So delta x, right? Delta x here, delta x here, delta x here, delta x here, and you have some curve. And instead of picking the point to the right of your delta x region, you pick the point to the left of your delta x region, and then you draw a rectangle. And on this next one, this is the left point of this next region, so I drew a point there. This point right here is to the left, so I drew a point there. And then if I go up, this point is to the left of this delta x region here. So this is the left-hand rule. You pick the left side of your delta x region rather than the right. And essentially you do the same thing. Find the y values of each of the points and then multiply them by height times width to find the area of the rectangles. Well, how about for midpoint rule? Well, midpoint rule, very, very similar, again, to the right and left rule. But basically, midpoint rule is slightly different in a way. It's a little more tedious to solve, actually, I'd say. But your delta x, idea of delta x would be the same, right? And the idea of and instead of using the right or the left sides of your region, well, hence the name, use the middle, midpoint. So this is right in the middle of delta x, in the center of your region, and then you draw rectangles to the left, and you draw your rectangle to the left and to the right of your region. So this right here, midpoint, I draw a rectangle. Go to the middle of this region, all right, midpoint, draw a rectangle, and so on. So this is midpoint rule. Well, what about trapezoidal rule? Well, trapezoidal rule is essentially an average of your right and left Riemann sums. So if you calculate your Riemann sum using the right rule, if you calculate your Riemann sum using the left rule, and you averaged out those values, you would get the trapezoidal Riemann sum. Well, let's draw a trapezoidal Riemann sum along some curve like this. Maybe like this. Yeah, that looks better. And basically what the trapezoid does is, again, you pick some delta x. So let's draw the delta x's. And what you do with trapezoidal is pick your left or right rectangles carefully. Now the thing about your rectangles is you're going to be switching between left and right rectangles. Yeah. So sometimes you're going to pick the left side of your delta x, sometimes you pick the right. You pick the lower value of delta x in order to use the trapezoidal rule. So I used a left rectangle here, right? You pick the point to the left of your delta x. And what I'm doing is drawing a point to the right now and then creating a triangle between these 2 points. So you can calculate the height of this triangle by just subtracting the 2 y values of these 2 points. So this was y2 and this was y1. You can calculate the height by subtracting y2 from y1 of this triangle. And essentially, if you keep going on with the trapezoid, you draw a point on the left side of your x value, and you draw a point on the right side of your delta x. And you could draw a triangle between them. This triangle is going to be a really tiny triangle, but it'd look like this. And you draw the rectangle below the triangle. This is another trapezoid. You pick the point, draw the point to the left and to the right of the region. And the higher point is where you start the top of the triangle. You draw another triangle. And then you fill in the bottom with a rectangle. And you draw another point at the end of this function. Let's say this function goes up to like here or something. And if I pick the point, draw the point to the top, left and to the right, I just am drawing the triangle like so. So basically what trapezoidal does, create a bunch of trapezoids, and then you can find the area of the trapezoids by using your knowledge of the y values and the x values. So I wanted to do a quick cover on that. Let's treat this as y1 and y2. So the heights of these 2 points are treated as y1 and y2. If we subtract the height of y2 minus y1, as I said earlier, you get the height of this triangle. And the height of y1 in this case is the height of the triangle, is the height of the rectangle. So y1 is the height of the rectangle. And the width of the triangle and the width of the rectangle is simply delta x. So if I multiply delta x by y1, I get the area of this rectangle. And if I multiply, well, for this, if I multiply delta x times y2 minus y1 times 1/2, you get the area of this triangle. So if you could keep repeating this process throughout this entire time, you will be able to find the area of all the triangles and rectangles. Now, keep in mind, this is a very tedious method. I hate doing this. Matter of fact, doing antiderivatives will probably be easier than doing this. But, you know, for the sake of learning, I will make a video for you guys on this. But another way to solve for your integrals is using geometry. Before we move on to geometry, I forgot to add a very important part about Riemann sums. Basically, the smaller delta x's, or the more rectangles you have, the better of an approximation the Riemann sum is. So basically, the smaller these rectangles are, the thinner they are, As it gets super, super thin, you get a better and better approximation of your actual integral or area under the curve. Now, hypothetically, what if your delta x approached 0? So what if the limit as delta x approaches 0? So these get infinitesimally small, like this small, and even smaller and smaller and smaller. Well, essentially, you just get a bunch of lines, really, really tiny, thin, super, super thin rectangles, right, under your curve, and that is the heart of an integral. The integral makes it so that your rectangles get infinitesimally thin. And when you add up all those areas of all the infinite rectangles, you get the true integral, or the true area under the curve, instead of using approximations like Riemann sums. But let's go ahead and talk about geometry. So in the case where the function is very easy to solve for using geometry, you can just simply use geometry. Well, if you wanted to solve the integral of, let's say, from this within this domain, well, simply for this function, so let's call this function just x. It's just a linear line with a slope of 1 starting at the origin. If you wanted to find the integral between these two yellow lines, right, you calculate integrals between regions on your function. Then you could simply use the formula for a triangle, right? If you knew the length of this region, say the length of this region is 3, then you can plug in for x equals 3 at this point here. You can find the height of your triangle, which is equal to your function at x equals 3. And when you just multiply f of 3 by your base times 1/2, you get the area of some triangle. And in this case, if the function was x, then if you plug in 3 into x, you just get 3. So 3 times 3 is equal to 1/2. What times 1/2 is equal to 9/2. So the area of this region is 9/2. So geometry can help you sometimes when you have something that's really easy. You could also say if you had a function where there's a semicircle, and then now you had a box here, and then you had a triangle, right? Not really a real function because you have vertical lines in this case. Actually, let's make it a triangle instead. So you have a real function. But for this function, if you knew the radius of this, then you'd be able to calculate the area of this semicircle. And if you knew the heights of this triangle and the base lengths, then you'd be able to calculate the areas of these triangles as well using geometry. But then again, geometry, super unreliable method. You're like the only time where you're really going to be using geometry on a test is when they're going to give you a picture of the function rather than the actual function. And the function tells you some radius, some base length, or some height of triangles and semicircles on it. It's actually kind of useful to get to know this, but let's go ahead and talk about antiderivatives, the actual true blue way to solve for integrals. So what is an antiderivative? Well, an antiderivative is what the name states. It's the opposite of a derivative. So if you had some integral of some function, an indefinite integral, so you don't actually get a whole number area for this, you get an equation to find the area. And this is the integral symbol, and this dx is your infinitesimally small delta x. I'll cover that in a couple seconds, but first off, let's do this. So the integral of your function is equal to capital F plus some arbitrary constant. You don't need to worry about this arbitrary constant right now. I will show you that in another indefinite integral video. But in essence, arbitrary constant is something that you lose when you take a derivative. So the antiderivative, or the integral, is equal to capital F of x. Well, in essence, basically, the derivative of your function f of x is equal to your original function. So if I were to give you an example of this, if your original function was x, right? If your original function was x, then that means the derivative of your integral should equal x. Well, the derivative of your integral is, or your integral for x is x squared over 2. And if you found, let's call this capital F, is equal to f of x. If you found the derivative of capital F, let's take derivative of capital F, you would get x. And the derivative of capital F, remember, is equal to your function. So your function is what you're trying to find the area under. This is the function that you're going to be using for your area between your x-axis and the curve. And the capital F function will give you a function that tells you the area under the curve based on the x value you plug into that function. Now, there are other things that you need to know about integrals, but that's an entirely different video. I don't want to make this thing stretch 30 minutes. So, in essence, this is called an indefinite integral. It doesn't actually give you an area. It just gives you a function to find the area. Now, let's go ahead and talk about this dx here. Now, this dx isn't that important for you guys yet. Calculus 1, it's not that important. Calculus 3 gets pretty important. But, in essence, if you see a t, if your t is the variable for your function, then you just write dt. If a is the variable for your function, then you write dA. Right? And basically, your dx is your infinitesimally small delta x. So remember, we would pick a delta x for your Riemann sums. And we covered that if the limit of delta x approaches 0, so if this gets super, super small, to the point where you just get a bunch of lines to find the integral, then this right here, this really tiny delta x is equal to dx. But you don't need to worry about the actual concept of that too much in Calculus 1. You're not really going to be doing anything with that. Just keep in mind that keep the variables consistent. If you have a t as your function, you write dt as well. So if I wanted to introduce the idea of how to solve for antiderivatives, I already kind of gave you a gist of it, but you have to use things like inverse power rule. Inverse power rule. That's going to be the main one you're going to be using in Calculus 1. You're also going to be using the inverse trig and trig function integrals. And you're also going to be using U substitution, which is the kind of inverse chain rule of your integrals. Now, inverse product rule and inverse quotient rule, stuff like that, I don't even think there's an inverse quotient rule. I have no idea. But like the product rule version of an integral is covered in Calculus 2. So you don't have to worry about that. You just worry about U substitution and inverse power rule. And the trig ones will come with just practice. But let's go ahead and do some. Let's do a trig practice right now. What is the integral of sine of x? Well, remember, the derivative of your integral is equal to your function. So we need to find a function where the derivative of the function is equal to sine of x, and that's cosine of x. And we're adding the arbitrary constant. Just put a plus c after every indefinite integral. You don't have to worry about the terminology of that too much yet. I'll cover that more in depth again in another video. But in essence, this function right here, this function's derivative, this is f prime, this is capital F, sorry, is your integral, or your indefinite integral function. And if you were to take the derivative of f prime, so if you were to take the derivative of, sorry, not f prime, why do I keep saying f prime? Capital F, negative cosine of x, plus c. Well, you take the derivative of some constant, it just cancels out, so we don't worry about this. If you take the derivative of negative cosine, you get negative sine of x, right? And you just get your original function, sine of x. So the derivative of your integral is equal to your original function. Keep that in mind. That's the essence, the total, the true whole wraparound of integrals. But I think I've covered enough today. Honestly, it just requires practice, just like derivatives do. But it requires like more reverse thinking. But as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.